In 1971, I was a member of a group of scientists who proposed a 5-year research effort towards the demonstration of a large vocabulary connected speech understanding system. Instead of setting vague objectives, we proposed specific performance goals. The proposed speech understanding system was required to accept phrases and sentences from many speakers based on a 1,000-word vocabulary using a task-oriented grammar within a constraining task. We wanted the system to perform with less than 10% semantic errors, using about 300 million computer instructions per second of speech. Although these goals were highly ambitious at the time of our proposal, we felt that the required system could be demonstrated within 5 years. The Harpy system, developed at Carnegie Mellon University, not only satisfies these goals, but exceeds some of the stated objectives. It recognizes connected speech from male and female speakers using a 1,011-word document retrieval task. It achieves 95% semantic accuracy and runs an order of magnitude faster than expected. Harpy is all the more interesting because it is one of the few examples in artificial intelligence research of a 5-year prediction that was, in fact, realized.
I am interested in speech understanding.
Harpy is the result of combining and improving the best features from 2 speech systems previously developed at Carnegie Mellon University, Hearsay 1 and Dragon. 2 features of the Harpy system that led to a successful demonstration are its representation of knowledge and the use of new search techniques. In developing speech recognition systems, it is necessary to devise a means of acquiring and representing the many diverse types of knowledge that characterize speech. We must also develop matching and search techniques that convert this passive knowledge into an active process for understanding and utterance in the presence of error, noise, and uncertainty. First, let us consider some aspects of knowledge representation. The document retrieval task we saw earlier uses a vocabulary of 1,011 words. When a user speaks to the system, his utterance must conform to the grammar and vocabulary for that task. Internally, Harpy stores all legal sentences in a finite state graph structure. Here is a graph of a simple grammar. This knowledge is organized as a network of nodes where each node holds a word in the vocabulary. The nodes are interconnected such that any path through this word network constitutes an acceptable sentence.
Tell us about Nixon.
Give me the headlines.
Tell me all about China.
Many words have more than one acceptable pronunciation.
Vodka and tomato juice.
We don't have any tomato juice.
What? The next time the hot tomatoes are in town, you better have tomato juice.
Alternative pronunciations can be represented as a separate network of acoustic gestures called phones. Phones are the smallest elements of speech knowledge represented in the Harpy network. Each path through the network represents an acceptable pronunciation of a word.
Tomato.
Tomato.
Dialects and accents can also be integrated into these pronunciation networks as separate paths. This is the pronunciation network for the word tell.
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 The pronunciation network for tell is really a further specification of tell in the word network. Thus, we can replace tell in the word network with its pronunciation network. Likewise, replacing every node in the word network with its pronunciation network generates a new finite state graph where each path is a pronunciation of an acceptable sentence.
Tell me all about China.
The substitution of pronunciation networks for words adds a second level of knowledge to our graph. Another aspect of speech knowledge involves the phenomena that occur at word boundaries. In written text, word boundaries are clearly defined by spaces.
Tell me all about China.
In spoken language, word boundaries tend to overlap, making it difficult to detect the end of one word and the beginning of the next. This problem is similar to writing, tell me all about China, without spaces or with spaces within words. As a result of this, complex phenomena arise where phones are inserted or deleted at word boundaries. Knowledge about such phenomena can also be represented in a Harpy network. This third type of speech knowledge completes the Harpy network representation. The overall size of the network is reduced by special heuristics. This is achieved by detecting and removing redundant paths. A separate knowledge network is compiled for each Harpy task. This eliminates the need for dynamic interpretation of knowledge during the recognition process. The finite state representation makes it possible to store knowledge of grammar, vocabulary, pronunciation, and acoustic phonetics in a single network. Let's consider how this knowledge is used in the recognition process.
Tell me all about China.
When an utterance is input to the computer, several pre-processing steps are taken to prepare the data for recognition. The utterance is digitized, segmented into acoustic units, and analyzed to determine the segmental features and parameters. This utterance has been divided into 23 segments. At this point, an attempt is made to match the first segment with one of the 98 possible phone labels. Since an absolute assignment cannot be made reliably, the system calculates a match probability based on the acoustic information in each segment. Thus, the silence phone is given the highest acoustic match for this segment, then the K phone, then TH, and so on. As the acoustic matches are generated, Harpy begins the recognition process. The goal of the recognition task is to find an optimal sequence of phones satisfying two criteria. The sequence must represent a legal path through the knowledge network and should consist of phones with high acoustic matches. Harpy uses a beam search to locate this optimal sequence of phones. This is a search technique in which a group of near-miss alternatives around the best path are examined. By searching many alternatives simultaneously, the beam search eliminates the need for backtracking. The search is executed by creating and examining a tree structure of phones whose connections are consistent with transitions in the knowledge network. Each ply in the recognition tree represents one segment of the digitized utterance. Harpy begins the beam search by taking all legal phones for the start of a sentence from the knowledge network and entering them in the recognition tree. Next, a path probability is calculated for each candidate. This is a cumulative value based on the path probability for the previous node and the acoustic match probability of the current node. The path with the best probability is determined, and remaining candidates are compared with it. Those that fall below a threshold of acceptability are pruned from further searching. The successors of the surviving candidates are expanded based on the information in the knowledge network, and the search continues. When paths are expanded, two phones may generate the same successor. Instead of retaining two independent paths through the same node, we can collapse them into a common path, avoiding redundant computation. Only the path with the highest prior value is relevant at this point. Thus, lesser value paths can be discarded because their path probabilities can never exceed the one with the highest value. The path probabilities are calculated as before, the best path is established, and unpromising alternatives are pruned. The forward search continues, expanding the recognition tree and saving those connections that satisfy the threshold until we reach the end of the utterance. Of all the paths that survive to the end of the utterance, the one with the best path probability is the solution that we are seeking. This is the only path that satisfies the two criteria of the recognition process. It provides the best interpretation of the acoustic matches while satisfying the constraints of the knowledge network. A backtrace through the recognition tree reveals the desired solution. This is purely a lookup operation and does not involve any search. What appears to be the best choice in the forward search may not in fact be part of the overall solution found by the backtrace. Thus, errors introduced by the acoustic matches are easily recovered by delaying commitment to a particular path until the forward search is completed. Thus, the forward search may be errorful without affecting the final solution. Let's look at the recognition process again as it occurred on the computer.
Tell me all about China.
The utterance is digitized, segmented, and acoustic matches are generated. The 4 words with the best path probabilities appear below each segment. The backtrace selects words leading to the optimal path. This is an example of Harpy working with a very simple task grammar. Let's look at the system's performance on several complex grammars.
Land subject to inundation. Point. Okay.
Speech understanding systems offer 2 advantages. They allow humans to communicate in a natural manner
Highway, double line.
and free their hands for other work. The cartography task requires vocal identification of topological features as they are traced into the computer.
What is beta times gamma?
This is an example of a desk calculator task. The speaker requests arithmetic operations to be performed by the computer.
Do any papers discuss hill climbing?
This is an example of the 1,000-word document retrieval task. The knowledge network for this task contains over 14,000 nodes. It is the largest task currently running on the Harpy system.
Knight to King Bishop 3.
Here is an example of a voice chess system. The player speaks his move to the computer in standard notation.
Springer F-Dry.
When the system is confronted with an utterance that is inconsistent with the task vocabulary, it still searches for the optimal path. However, when the overall path probability falls below an acceptable threshold, the recognized utterance is rejected.
By combining the best features of earlier systems, Harpy is able to recognize speech faster and more accurately. Since the end of the 5-year project, the system has been further improved and at present runs an order of magnitude faster. The two features of the system that contribute to Harpy's success are its representation of knowledge and the beam search technique. By pre-compiling all the diverse sources of knowledge into a single integrated network, Harpy achieves a level of efficiency that is unattainable by systems that dynamically interpret their knowledge. This permits Harpy to consider many more alternatives and deal with error and uncertainty gracefully. Backtracking and redundant computations have always been problematic in AI systems. The Harpy system eliminates both of these in an elegant manner. It is not always possible to capture all the language constraints as a finite state graph. A graph structure that attempts to represent every possible variation requires a great deal of memory. More compact representations of knowledge involving a greater degree of dynamic interpretation can certainly be used in Harpy-like systems. This is purely a space-time trade-off. Occasionally, the heuristics associated with the beam search miss the optimal path. But because the acoustic matches are less than accurate, attempting to find the optimal path at great cost and effort leads to little or no improvement in the overall performance. Everybody is an expert in speech, and so we naturally expect flawless performance from the computer. However, given the immense complexity of the task, we must continue to build more and more complex speech understanding systems so that we may one day have systems approaching human performance. Continued research in this area will also teach us how to build complex knowledge-based systems and provide us with a deeper insight into the nature of intelligence.